What was the Earth like 2 billion years ago? If you took a time machine back to about 4.5 billion years ago, when Earth was just starting to form, you would probably regret it. Large parts of the Earth's surface would still be molten, making it very dangerous to land your time machine. Early Earth was a dangerous place, so buying a time machine isn't something to do on a whim. Why was the Earth back then so nasty? Let's find out. Hello viewers, welcome to our channel. In today's video, we will travel back in time 2 billion years to explore the Earth. Are you guys excited? I'm sure you are. But before we get to the video, make sure you hit that subscribe button and turn on the notification bell so that you will never miss any of our videos. When life first appeared on Earth billions of years ago, the atmosphere was quite different from what it is today. Carbon dioxide, nitrogen, and a number of other gases were present in the primordial atmosphere of our planet, and these elements made life as we know it impossible to exist. However, by the time of the Paleoproterozoic era, 2.5 to 1.6 billion years ago, a significant change that is now known as the Great Oxidation Event had taken place, which involved the introduction of oxygen into the atmosphere, GOE. Both the natural decay of radioactive elements present on Earth and the processes associated with the planet's formation contribute to the planet's overall temperature. The Earth's structure was significantly altered as a direct result of the heating. During the course of its development, the Earth amassed a variety of rock silicate mineral grains in addition to iron and nickel. These materials were dispersed across the surface of the Earth. That changed when the Earth began to heat up. It became so hot that the metals melted and trickled down through the rocky silicate material toward the center of the Earth, where they eventually formed the core of the Earth. In other words, the Earth reverted back to its original state, the process of silicate materials and metals becoming differentiated into a rocky outer layer and, respectively, a metallic core is referred to as differentiation. The friction caused by metal melts moving through the Earth caused an increase in the temperature of the planet. Because of the higher temperatures that existed in the early stages of Earth's history, early tectonic processes occurred at a more rapid pace than they do now, and the surface of the Earth was more geologically active. Even though the Earth had sucked up a significant portion of the material in its orbit as it was accreting, there was still a great deal of unrest within the solar system caused by changes in the orbits of Saturn and Jupiter that was sending a great deal of large objects on potentially catastrophic collision courses with the Earth. The energy released from these collisions repeatedly melted and even vaporized the minerals that make up the crust of the Earth, as well as blasted gases out of the Earth's atmosphere. Even though they are old, the scars left behind by these collisions can still be seen, but we have to look very closely to find them. For instance, the quote-unquote crater at Maniitsoq in West Greenland, which is estimated to be 3 billion years old but does not actually contain a crater, is the oldest impact site ever discovered. What can be seen are rocks that were buried between 20 and 25 kilometers beneath the surface of the Earth at the time of the impact, but which nevertheless show signs of deformation that could only have been produced by a severe and sudden shock. The evidence of the most catastrophic collision that Earth has ever been subjected to is not in the least bit subtle. In point of fact, it is highly likely that you have already looked directly at it hundreds of times, although you may not have been aware of what it is. This collision took place with a planet known as Theia, which was roughly the same size as Mars. Theia struck Earth not long after the formation of the planet. When Theia collided with Earth, its metallic core merged with that of Earth, and debris from the planet's outer silicate layers was ejected into space, where it accumulated to form a ring of rubble that encircled the planet. The material that was contained within the ring eventually consolidated into a new body that went into orbit around Earth, which we know now as our moon. It's remarkable to think that the debris could have accumulated in as little as 10 years. The term giant impact hypothesis refers to this proposed explanation for how the moon came into existence. The first attempt by Earth to create an atmosphere did not meet with any degree of success. It began with a very thin layer of gases composed of hydrogen and helium, which were brought along by the material that it created. Hydrogen and helium are extremely lightweight gases. Consequently, they were able to escape into space. The second attempt at giving the Earth an atmosphere ended up being a lot more successful. Eruptions of volcanoes release gases into the atmosphere, which contribute to the thickening of the atmosphere. Water vapor and carbon dioxide, CO2, are the two gases that are released by volcanoes the most frequently. However, volcanoes can release a wide range of gases. Other important contributions include methane, hydrogen gas, sulfur dioxide, carbon monoxide, and hydrogen sulfide, or H2SCH4. In addition, meteorites and comets were responsible for the delivery of significant quantities of water and nitrogen to Earth. Carbon dioxide, water vapor, and nitrogen were probably the three most abundant components after Earth's second experiment, but it is not clear what the exact composition of the atmosphere was at that time. One thing that we are able to state with absolute certainty about Earth's second experiment is that the atmosphere did not contain any detectable levels of free oxygen. This is one of the ways in which we have established this fact. Prior to 2 billion years ago, there were no red rocks that were colored by oxidized iron minerals. There was evidence of iron minerals, but they were not in an oxidized state. Back then, the sun's ultraviolet rays would break apart water molecules, which would result in the production of oxygen gas in the atmosphere. On the other hand, the oxygen wasn't around for long because chemical reactions removed it just as fast as they produced it. Oxygenation of the atmosphere did not occur until well into the third experiment that Earth was conducting, which was the evolution of life. Photosynthetic organisms use the abundant CO2 in the air to manufacture their own food, and as a byproduct, they released O2. At first, all of the oxygen was used up by the chemical reactions as it had been in the past. However, eventually the organisms released such a large quantity of oxygen that it overwhelmed the chemical reactions. The atmosphere started to become increasingly rich in oxygen, but it wasn't until about 350 million years ago that it reached its current level of 21% oxygen. Nitrogen makes up a significant portion of the portion of our atmosphere that is not oxygen at the present time, 78%. The telltale sign that life exists on our planet is the oxygen-rich atmosphere. If geological processes were the only thing that controlled our atmosphere, it would be dominated by carbon dioxide just like Venus' atmosphere. The idea that for the past 2 billion years, the light reflected from our planet has been beaming a barcode out to the universe is one that can be considered fascinating, or unsettling depending on your point of view, but either way, it is an intriguing concept. For the past 2 billion years, our planet has been transmitting a signal into space that, if received by an observer from another world, might make them think, that's odd, I am curious as to what is taking place over there. Alright guys, that's it for today's video. If you enjoyed this video and want to watch more videos like this, then hit the subscribe button and ring the bell icon so that you will never miss any updates.